Hi everyone, so for this discussion, this is 9.4, discussion on the models of population growths. And the one we discussed last time from 9.1, let us recall, is P of t equals P naught e to the kt. We saw this before, and this satisfies this differential equation, this satisfies this initial condition, P of 0 equals P naught. Now instead we're going to look at something a little more realistic, that happens naturally basically. It's called the logistic model. And it will satisfy the original differential equation dp dt equals kp, but it'll approximately be that. So it won't be quite that, but it'll be approximately that when p is small. So it'll start off exponential, but then it'll slowly approach a halt basically. And the halt that it'll approach is called the maximum carrying capacity. So the carrying capacity is basically the maximum population size. And that's going to be m. So this m here is the largest p can be, and of course p is going to be in between 0 and m because we don't want a 0 population size or a negative population size. And notice that this differential equation will actually work for us because when p gets closer to 0, this will approach 1, and we'll just get the original differential equation we saw last time from 9.1. But as p gets closer and closer to m, well, this will approach 1 minus 1, which is 0, so that means what the rate is going to do is also approach 0. So essentially what we'll get is this following model. It will look something like this. So as t is time, and this y-axis here represents our population size, we're going to get as a horizontal asymptote here, and this is going to be m. So it's going to approach m, so it's going to start off exponential at some point, and then slowly get closer and closer toward the carrying capacity. So now what we're going to attempt to do here is we're going to attempt to solve this differential equation, and of course we're going to do that by means of separation. This is of course separable, by the way. There's no t in sight, so everything here involves p. We'll move it over to this side. We'll have to divide. It's going to be a little tricky, but let's see if we can do it. So I'm going to divide by p, so it's 1 over p. And then we'll have to divide by this. Let me do this. Let me write this as m minus p over m. Of course, we're allowed to do that because 1 is 1 over 1. So if you multiply top and bottom by m, 1 minus p over m ends up being m minus m all over the common denominator m. Okay? So now, dividing by this to both sides, it'll leave us with 1 over p times the reciprocal of this, which is m over m minus p. dp is on the left still. I'm going to leave k over here on the right, multiply by dt, and we get this. Now what do we do? Well, now we've separated the variable, we separated the equation, and we can integrate. Remember, m is a constant, k is a constant. On the right, we just get kt plus a constant t. On the left, we can pull out m, I guess. And it becomes a little less clear what we're going to do here, but if you take a look at it, what it should remind us of anyways is, that's right, partial fraction decomposition. Because the denominator is p times n minus p, so we can actually break this up as something over the first factor plus something over the second factor. We can attempt to solve for a and b, and we'll see that right now. Okay, so now here we're going to attempt to combine this into one fraction, and we will get a times m minus p plus b times p all over the common denominator p times m minus p. And that's of course going to be equal to the original fraction. And what you'll notice is that of course, since the denominators are the same, the numerators have to be the same. So we can actually just write a times m minus p plus bp is equal to 1. Okay, great. So now we can, p is our variable here, so we can set p to be different things. So if we set p equals to m, that'll make the first term go to 0. P minus p will be 0, so we'll get nothing here. Plus b times m, because p will be m, so it's bm is equal to 1. Okay, great. Dividing by m, we get b is equal to 1 over m. And now we'll plug in something else for p. What can we plug in for p now? I guess if we plug p to be 0, what do we get? Well, if we plug in p to be 0, now we'll get a times m. b times 0 will be 0, so that's going to be equal to 1. Dividing by m now, we'll get a is equal to also 1 over m. It's kind of suspicious looking, but I like it. Okay, so what we've discovered is that a is 1 over m. b is also 1 over m. And if you pull 1 over m out of the integral, remember this is still inside of the integral dp, well, it'll cancel out this m, won't it? So if you pull 1 over m out, you just get this. And the m's cancel. Perfect. Now we can antiderive each of these. Notice we're antideriving with respect to p. So the antiderivative of 1 over p is going to be ln of p. The antiderivative of 1 over m minus p is also going to be ln of m minus p. But since the derivative of m minus p with respect to p is going to be 0 minus 1, you have to divide by negative 1 on the outside. In other words, if you were to actually do this by u substitution, notice u will be equal to m minus p, du will be negative dp. So what this integral will turn into, essentially, is negative 1 over u du, because of the du being equal to negative dp. So a negative comes out. So we end up getting this. Okay, so now I've cleaned some things up here, and what we're going to do now is we are going to, well, I'm going to apply an ln property, log property basically. Ln of something minus ln of something else is ln of the quotient, first divided by second. And then this side stays the same. Okay, now we're going to get rid of the ln by taking both sides as powers of e. E to this equals e to this, so lowering the equality symbol. Remember, e to the kt plus c is e to the kt times e to the c. And e to the c is just a new constant, reset it as c. Okay, so now what we'll end up with is these cancel on the left. We'll ignore the absolute values because of reasons we saw from 9.1. We get p over m minus p is equal to c times e to the kt. Okay, and now is an okay time to solve for c, but I'm actually not going to, not yet. There's something else I kind of want to get out of the way. Let's completely solve for p first, and then we can worry about the constant. Yeah, how do we do that? Well, I'm going to reciprocate both sides to get p by itself, and the thought process there is the following. P over m minus p, p is in two locations, on top and on bottom, right? Now, you can't split this fraction up because the denominators are different, it's not the numerator. But if you flip it, you get m minus p over p. This can be split up, and you get m over p minus p over p, which is just 1. The benefit of this is that now we have p only as one in one location, and we can solve for p more easily. So let's see that over here. If we reciprocate both sides of this equation, on the left we get m minus p over p. On the right, it looks a little funny, but here's what you're going to get. We're going to reciprocate this whole thing. So when you reciprocate this, you get 1 over c times 1 over this. So think of it like this. 1 over c e to the kt is the same as 1 over c times 1 over e to the kt. Right? Reciprocal of product is the product of reciprocals. So 1 over c, I'm just going to call c, because 1 over a constant is still the constant. 1 over e to the kt, I'm going to write that as e to the negative kt, because negative power means reciprocal. Okay? Great. And now what? Oh, now we can separate this just like we said earlier. That's the whole reason why we're doing this anyways. We get m over p minus 1 is equal to c e to the negative kt. Maybe now is an okay time to solve for c, but I still want to keep going and solve for p completely. We're so close, what can we do? We can just add 1 to the other side. Oh, look at that. And then reciprocate both sides now to get p on top. So p over m is equal to 1 over 1 plus c e to the negative kt. Now finally, multiply both sides by m. We'll get p is equal to m over 1 plus c e to the negative kt. Now this is basically the final answer. The only thing is, and you'll see this if you look in the book refers to this C as capital A. So I'm calling it C, but the book calls it capital A. And whatever you want to call it, I guess we'll go with the book and call it capital A. We'll solve for that right now. Okay, so now using our initial condition, P of 0 is equal to P naught. Remember that 0 is T here, and this is our P value. So that when T is 0, P is P naught. So we're going to apply that. So we're going to let T equal 0, and we're going to get the following. P, remember, is P naught when T is 0, equals M over 1 plus A e to the negative k times 0. E to the 0 is 1, so really we get just P naught is equal to M over 1 plus A. So now let's solve for A, and I'm going to do the same tricks I've been doing. Reciprocate both sides. We'll get 1 over P naught is equal to A plus 1 over M. Multiply by M. So M over P naught is equal to 1 plus A. Subtract 1 to both sides. So A is equal to M minus, or M over P naught, I meant to say, minus 1. We can combine the right-hand side to get the following. A is equal to M minus P naught all over P naught. Because of course 1 is 1 over 1, which is P naught over P naught if you find a common denominator. There we go. So now plugging this back in, we can get something a little maybe better to look at, but it's going to look a little weird, honestly. The book just leaves it at this. They say that the solution is P of T is equal to the max capacity over 1 plus A times e to the negative kt, where A is equal to this. And that's kind of like where we're leaving off right now. I'm going to do an example involving this right now. Okay, so for this next example, we're given a particular differential equation. dp dt is equal to 0.08p times the quantity 1 minus p over 1,000. The initial condition we're given is a p of 0 is 100, so that's the initial population size. And we want to use this to find the population sizes p of 40 and p of 80, so p at time 40 and p at time 80. And then next we're asked, at what time does a population reach the size of 900? And what's interesting here is we can actually use what we've already discovered. That's why I left it up here. So labeling things correctly, this is K. Notice if we compare to this, K are, let's see if I have things written correctly. Yeah, I don't know why I wrote this as M over P. This is supposed to be P over M. That was a mistake before, but it doesn't actually affect this solution. I just rewrote it wrong for some reason, but it doesn't matter. Looking at this, this is M. So that's our max capacity. And yeah, that's our initial population P0. And we can actually use this information to just find our initial, well, to find our solution. And I guess what we can do is just modify this. So here's what I'm going to do. I was going to pause the video and fill this in, but let me just do it live now. So what's M? M is 1,000. What's A? Well, A is going to be this. So we'll do that in a second. But first let's fill in K. So K is 0.08, so that's going to be negative 0.08 times T, where A is this. Now remember, M is 1,000. The population size, the initial population size is 100. So it's 1,000 minus 100 over 100, which is 900 over 100, which is just 9. So A is 9, and since A is 9, we can fill it in to be 9. So this actually is the solution to that example. Pretty crazy, without even doing any differential equations. We already solved the general case. And now we can use this to find the population sizes P of 40 and P of 80. Just plug in 40 and 80 for T. We'll do that right now. Okay, so now to find P of 40, all we're going to do is plug in 40 in for T. So we got 1,000 over 1 plus 9 e to the negative 0.08 times 40. Now all I'm going to do is just apply my calculator. Well, plug this into the calculator, and what it gave me was 731.6 about. And all I'm really doing is just plugging this in. I'm not even playing around with the mathematics of it. There's a little bit you can say possibly, but just plug it in and you get this. That's fine. Okay, so what about P of 80? Well, P of 80, again, similar thing, you're going to plug it into this. So without me even writing it out, just using my calculator, I got 985.3 if you round. And now we're moving on to the next part of the question, which asks us, at what time does the population size reach 900? So let's see that right now. Okay, so when the population size is 100, we want to find t. So we're going to let P of t be 900. And we're going to attempt to solve for t in this case. And can we do it? I believe we can. This involves a lot more math than the previous two things we found. Well, here's what I'm going to do. I'm going to multiply both sides by this denominator and simultaneously divide by 900. Basically, I'm going to swap these two. And we're going to get the following. 1 plus 9 e to the negative 0.08t is equal to 1000 divided by 900. And this is a trick you can do in proportions. Basically, I'm saying that if a is equal to b over c, multiplying both sides by c and then dividing both sides by a just gives us c is equal to b over a. So all we've really done is swapped a and c. So we're just multiplying and dividing basically. In any event, here we can cancel two zeros, we get 10 over 9. Okay. Subtract 1 to this side to get rid of the plus 1 part. Okay, so far so good. 1 is 9 over 9, just to get a common denominator. So it's going to be 1/9. Okay, so far so good. Now divide both sides by 9. We get e to the negative 0.08t is equal to 1 over 9 divided by 9 is 1 over 9 times 9, which is 1 over 81. Okay, to get rid of e, much like getting rid of ln, to get rid of ln you take both sides of powers of e, but vice versa, to get rid of e, you take ln of both sides. So if you take ln of the left and set that equal to ln of the right, run out of space a little bit. There we go. On the left, the e and ln cancel and you just get negative 0.08t. On the right, ln of 1 over t, remember our trick. When you have ln of something minus ln of something else, it's ln of the quotient. Similarly, if you have ln of a quotient, you can write that as ln of the top minus ln of the bottom. The benefit here is that what's ln of 1? ln of 1 is 0, because e to the 0 is 1. So this is ln of 1 minus ln of 81, which is just 0 minus ln of 81, which is just negative ln of 81. Now we can, cancel the negatives. Then divide both sides by 0.08, so we get t is equal to ln of 81 divided by 0.08. There's a little more you can do here, but all I'm going to do now is just plug it into my calculator, and let me see what I get. Okay, so I got 54.9, if you round. So that's the time at which the population size reaches 900. Now what's interesting about this question is that there's no context at all. I don't know if this time is represented in years, hours, minutes, seconds. I don't know if the population size is people or bacteria or whatever the case may be. But in any event, that's how these things behave. And I was going to stop the video here, but actually I'm going to do a homework problem. I assigned numbers 1 and 7, so let's take a look at 1 right now. Okay, so for this problem, homework problem number 1 that I've assigned, it's actually fairly straightforward and fairly similar to the previous example we just did. So we're given this differential equation in this initial condition, and I've written here in red that t is in weeks, which is what the problem gives us. And there are 3 parts of the question, which seems a little intimidating, but believe me, it's not that bad. A asks for the carrying capacity, which is m, so I just wrote what is m. And then they ask for the value of k, so we need to find what k is. B is asking us to find the solution, and then C finally is asking for the population after 10 weeks. And we can do this all right now in the space we have. To be honest, it's not that bad. Let's just label a few things. So remember how we did the last problem? We noticed that this is K and this is M. So we actually know A right away. M is 1200 and k is 0.04. Perfect. So A is done. Box those up. Perfect. Now write the solution. We also know the general solution. What is the general solution? Well, it is P is equal to the max capacity, 1200, over 1 plus A, which I'll talk about in a second, times e to the negative k, so negative 0.04, times t. Great. But now what is A? Well, remember A is the max capacity minus the initial population size over the initial population size. So in this case, it's going to be 1200 minus 60 over 60. And if you split this up, this is 1200 over 60, minus 60 over 60 is 1. There's cancellation of zeros here. 12 over 6 is 2, so 12 with a 0 over 6 is 2 with a 0, so it's just 20 minus 1. So A is 19. So all I have to do is replace this A with 19, and that's the answer for part B. Great. But now what about C? C asks the population after 10 weeks. All we're going to do is plug in T equals 10. So we want to find P of 10. And yeah, just plug in 10. We get 1200 over 1 plus 19 e to the negative. Well, look at this. 10 times 0.04 is just 0.4. Great. So now all I'm going to do is apply this on my calculator and see what I get. So let me type this up real quick and see what we get. Okay, so I typed it in and I got 87.4 if we round. And it doesn't say what the population is in. It doesn't say people or bacteria or whatever. I gave a few examples earlier. But anyways, this is the population size after that amount of time. And I also assigned 7. Let's just do 7. Alright, so now for number 7, like I said, this is suppose the population follows a logistic model and has initial population 1,000, carrying capacity 10,000, and they go on to say if the population grows to 2,500 after 1 year, what will the population be after another 3 years? And notice they don't give us k. We essentially have to solve for k using this. Now this is, it grows to this after 1 year. So they basically give us that p of 1 is equal to this. They also give us our initial population, which is p of 0. So I'm going to keep that in mind. Essentially, we're given 2 initial conditions. The funny thing though is we're no longer really solving a differential equation. We already have our general solution, the logistics model. And then after we find k using this, we want to find out what p of 4 is. Now they say after another 3 years, 3 years on top of 1 year is after 4 years total. Okay, so let's just try to apply some things here. So remember the logistics model is the max capacity, 10,000, over 1 plus A. Let's figure out what A is. Remember, A is a max capacity minus the initial population divided by the initial population. And again, if you split this up, you get 10,000 over 1,000 minus 1,000 over 1,000, which is 1. 3 zeros cancel, we get 10 minus 1, which is again 9. So that's plus A, which is 9, e to the negative kt. Perfect. Now all we need to do is find k using this guy here. And in fact, we can do that right now. Notice, when t is equal to 1, p would be p of 1, which is 2,500. So we get 2,500 is equal to 10,000 divided by 1 plus 9 e to the negative k. Because when t is 1, k times t is just k. Great, now we can solve for k. I need a little more space though. Okay, what's kind of clever here is we actually don't need our calculator at all if we're clever enough. You can still use your calculator if you like, but I'm not going to here. Let's just watch. It's actually pretty cool. So yeah, I want to solve for k, so I'm going to reciprocate both sides. Let's just swap these. Remember that trick? So we get 1 plus 9 e to the negative k is equal to 10,000 divided by 2,500. And 2 of the zeros cancel. We're left with 100 over 25, which is 4. To continue solving for k, we can subtract 1 to the other side. And what do we get? We get 9 e to the negative k is equal to 3. divide by 9. We get e to the negative k is equal to 1/3. Now at this point, we could actually, we could actually solve for k by taking ln, but what you'll end up getting is the following. You'll end up getting that k is equal to ln of 1/3. And remember that ln of 1 over something is negative ln of that something, kind of like we saw with the 1 over 81 situation. So k would just be ln of 3. And you can plug that in, but something a little more clever happens. We have e to the negative k is equal to 1 over 3. So if you think about it, our population model, P of t, is the carrying capacity 10,000 divided by 1 plus 9 times e to the negative kt. Now remember, e to the negative kt is e to the negative k to the t, like this. Since we know e to the negative k is 1/3, really what we're going to get is 1/3 to the t. Just like that. And now, what are we trying to find? We're trying to find p of 4. So we're going to plug in t equals 4, and let's see what we get. Okay, so now remember, we're asked to find p of 4, so plugging it in, we get 10,000 divided by 1 plus 9 times 1/3 to the 4. 1/3 to the 4th is 1 over 3 to the 4th. 3 to the 4th, well, 3 squared is 9. 3 to the 4th is that squared, so it's going to be 9 squared, which is 81. 9 over 81 is just 1 over 9, so there's some cancellation. And what we're left with is 10,000 over 1 plus 1 over 9. There's a lot we can do, but the best way, I think, to actually find out what this number represents is by clearing denominators, multiplying top and bottom by the denominator 9. So we get this times 9 over this times 9. Distributing that into the bottom gives us 9 plus 1, because 9 over 9 is 1. And then on the top we get, well, 10,000 times 9 is 90,000. So that's 9 with 4 zeros. Now, of course, 9 plus 1 is 10. So that's 90,000 divided by 10. So we basically just lose a 0. And the answer is 9,000 for P of 4. Beautiful. Doesn't involve any calculation using calculator. It's just all, you could do it all by hand, actually. So that concludes our discussion on 9.4. We did 2 homework problems, so it was a pretty good discussion, I'd say. And I'll see you guys in the next video.